Hello everyone, and welcome to another video. Today I'd like to delve deeper into our discussion and understanding of Bode plots by trying to understand how we can generate Bode plots of complex transfer functions. So if you remember, in some of our previous discussions, we discussed an introduction to Bode plots, things like resonant frequencies, as well as individual Bode plot components. So if you haven't had a chance to view these videos, please check out the description of this video for the URLs to some of this prerequisite material, and make sure that you review and understand those before continuing on. In our last video, we considered individual components of transfer functions by themselves. And while we gained some good insight to how an individual component of a transfer function, such as a single zero or a single pole, would contribute to a Bode plot by itself, I don't know the last time I saw one of these hanging out all by their lonesome, right? Transfer function components, they're like middle school girls, right? They don't hang out by themselves. They clump together to form more complicated dynamics. So what we really need to do is understand how can we take a complicated transfer function, break it down to its constituent components, and form the entire composition to generate a Bode plot of the overall more complex transfer function. So I think the easiest way to do this is maybe let's consider for a very simple general example. What if you had a transfer function, right, that was, you had a zero, right, but you also had a pole, right? This is a slightly more complicated transfer function than what we considered in our previous video, right? One thing to note here is you could write this, for example, if I factor this into standard Bode plot format, you could write this as z1 times s over z1 plus 1 all over P1 s over P1 plus 1. Or you could write this as just some gain k times s over z1 plus 1 all over s over P1 plus 1 here, where this gain k is now this constant value of z1 over P1. So here's our transfer function. So by looking at this, we see that this is actually made up of three components here, right? So the three components are, first we have a constant gain, right? That's this k term. This thing is also made up of a single real zero, right? That's this term here. And then the third component here is a single real pole, which is our last component here. So really we see that this transfer function, it's more complicated than one component by itself. It's actually three components combined together here. So the question is, can we leverage some of the material we developed earlier where we understand what does this component do to a Bode plot, what does this component do to a Bode plot, and what does this component do to a Bode plot, and compose them all together to get sort of this mega Bode plot, right? So the idea here is, if you remember with Bode plots, we first have to think about computing g of j omega, right? That's what this all came down to, right? Is looking at this complex number to understand the frequency, the steady state frequency response of the system here, right? So in this case, well, g of j omega, right? That's just k times j omega over z1 plus 1 all over j omega over P1 plus 1, right? And now the next step in the Bode plot, right, was understanding the magnitude and phase angle of this complex number. So let's just first consider, how about the magnitude of g of j omega, right? So the magnitude of g of j omega, right, it's just the magnitude of this complex number, right? So it's magnitude of k, and then maybe let's write it like this, j omega over z1 plus 1 times 1 over j omega over P1 plus 1. Would everyone agree that's the same thing here? Now, since we're only concerned about the magnitude of this complex number, what I can do now is everyone agree that this norm operation can just be distributed to these three products. In other words, this is the same thing as saying magnitude of k times magnitude of j omega over z1 plus 1, right, times magnitude of 1 over j omega over p1 plus 1. Right? Okay, and furthermore, if you remember from our Bode plot here, our Bode plot actually doesn't plot magnitude of g of j omega. We want to look at that in decibels here, right? So we want to look at what is, maybe let's write this down. So like, look at decibels, right? So we want 20 times log base 10 of magnitude of g of j omega, right? So it's basically, if you look at this, it's 20 times log base 10 of magnitude of k, right? Excuse me. I should have written this. Well, it's this entire thing here, right? And I guess I didn't manage the whiteboard space so well. This is magnitude of k times magnitude of j omega over z1 plus 1 times magnitude of 1 over j omega over p1 plus 1, right? Okay, and now if you remember how logs work, right, this is basically, if you recall, right, log base 10 of a times b times c. This is basically what? It's log base 10 of a plus log base 10 of b plus log base 10 of c, right? So if you apply that here, we see, let me go ahead and erase this side of the board so we have a little bit more space and we can write this out a little bit more cleanly, right? So again, the left side of this thing is 20 times log base 10 of magnitude of g of j omega, right? So now this is 20 times log base 10 of magnitude of k plus 20 times log base 10 of magnitude of j omega over z1 plus 1 plus 20 times log base 10 of magnitude of 1 all over j omega over p1 plus 1. Right? So if you look at this, let me maybe pick another color in green here. This is basically what? It's the magnitude contribution of component 1, right? Which we said was our constant gain. Right? And similarly, right here, this by itself, this is the magnitude contribution from component 2, right? Which was our real 0. And finally, this term right here is our magnitude contribution from component 3, which was our real pole. So this is fascinating here and super interesting. What we see here is that the components individually, to get the magnitude of the overall system, right? That's what the left-hand side of this expression was, right? This was the magnitude, I guess in decibels, right, of the complex transfer function. Right, our original g of s. So we see that, you know what? The complicated transfer function is nothing more than the linear addition of the individual contributions from each component here, right? So that is so important. I think we really should write this down here, is that when expressing magnitude in decibels, right? That's the key here, right? It's the log base 10. It's the 20 times log base 10 that allows us to do this. So when you express it in decibels here, right, the individual transfer function components they add linearly. So literally, all you need to do is figure out the contribution from this first component, the second component, the third component, and then just add them together here. And we're going to go through an example of that in a second, okay? So that's awesome. So the magnitude is really, really simple for a complicated transfer function. What about the phase here? How about let's consider the phase, okay? So the phase for a Bode plot, right, that was basically looking at the angle of g of j omega. right? Okay, so really we're looking at the angle of, what was j omega? It was, I guess we erased it here, but it's the thing inside the magnitude operation, right? So it's basically, I'm looking at the magnitude of k times j omega over z1 plus 1 times 1 all over j omega over z1 plus 1. Right? Okay, so it's the angle of this entire thing. Maybe let's put brackets around this here. Right? Now, here's the other thing that we want to remember here. So if you recall, the whole deal with complex numbers here is if you had an angle of a complex number times another complex number, a u times v, wasn't this just angle of u plus the angle of v? Similarly, you could also look at this as maybe angle of u over v, right, was angle of u minus angle of v, right, for complex numbers. So again, if you apply that here, we come up with a very, very similar idea here, right? This is just component times component times component, and apparently they just linearly add. So in other words, let's just go ahead and write that up here. On the other side, so the angle of g of j omega, right? In this case, it's the angle of k, right, which was this term plus this term, right, plus angle of j omega over z1 plus 1. Maybe again, let's put parentheses to capture that, right? Plus angle of 1 all over j omega over p1 plus 1. Right? So again, if you want to look at this in a similar fashion, right, this here is the angle from component 1, right, which was our constant gain, right? And then this term is angle or phase from component 2, right, which was our real 0. And finally, this one right here is the angle from component 3, right, which was our real pole. So again, what we end up here with is, oh, sorry, and again, maybe I just want to be consistent here. The left side, this is the angle of the complex transfer function, right, which was our g of s. So we see here the angle behaves the same here. So when expressing angle, again, it doesn't matter if you're doing this in degrees or phase here, right? The individual transfer function components right, they add linearly, right? So basically, we better box up these two results here, because this is the key here to understanding more complex transfer functions here, right? Is once you understand how these individual components, like a gain or a zero or a pole or an integrator or a differentiator or a complex conjugate pair, right? Once you understand those 7 components that we talked about in the previous lecture, any other transfer function, right, if you're expressing the Bode plot, it's just a linear addition of all of those different components here, right? So what we should do here is, tell you what, give me a second. I'm going to erase the board, and let's write down a cookbook procedure then of how we can go ahead and sketch and understand the Bode plot of a more complex transfer function. Okay, so let's go ahead and write down a procedure for how to basically sketch a Bode plot for a more complex transfer function. So what we're going to do here is, let's go and assume that you start with a transfer function. And let's write it down in sort of a general format here, right? Where it's basically just a numerator polynomial. Let's call it, bm s to the m plus bm minus 1 s to the m minus 1 plus all the way down to b1s plus b0, right? It's a numerator polynomial over a denominator polynomial, right? So an s to the n plus an minus 1 s to the n minus 1 plus yada 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 plus a1s plus a0, right? Numerator polynomial over denominator polynomial here, right? So you've got m poles and n zeros here, right? Okay, so the first thing you're going to do here, step one here, right, is we're going to factor this transfer function to identify the poles and zeros here, right? So I'm going to say factor transfer function to identify poles and zeros. Okay, so in other words, you want to factor this thing, the numerator and the polynomial, the numerator and the denominator, to look something like, you know, like a s plus z1, s plus z2, yada yada yada, all the way to s plus zm, right? And then similarly on the denominator, s plus p1, s plus p2, yada yada yada, s plus pn here, right? And what's going to probably happen is you're going to probably pop out some constant here on the top here. Let's call this thing alpha here, right? Now note this alpha is just a constant, right, to make this version of the transfer function equal to this version of the transfer function. However, this is not the constant gain that we've been talking about earlier here. So what I mean by that is, let's take a look at this in sort of our next step here, right? So now, step two is kind of the critical one here, and this is where a lot of people will make mistakes here. Okay, so what you want to now do here is you want to take this factored version of your transfer function here and basically write it in our standard Bode plot form, right? So write in standard Bode plot form. So just to refresh your memory here, right, the idea with that standard Bode plot form is we want to factor out so that all of these s plus z1s, I want ones everywhere. I want them to be like an s plus, you know, tell you what, instead of me talking about it, let me just show you what we're talking about here. So, okay, so g of s, right, it's still going to be, you're going to have this alpha term here, right? And then maybe let me write it like this. But this is going to be a little bit big, so maybe give yourself a little bit of room, because I want to write this in a general form, and then we're going to do it in a more normal fashion. So for example, this s plus z1, you want to factor out the z1 and pull it out here, and basically you get something like this, right? Would everyone agree that's sort of the same thing as this first term? All I did was kind of move the z1 outside here, right? And you would do the same thing with z2. Right, and then z2 comes out here, right? And you would do this for all of the sort of the real zeros here, right? So maybe what we should do here is, I'm going to say keep on doing this all the way down to s over z, maybe p plus 1, right? And then you get this zp, right? So these here are, you can sort of think of these here as your real zeros. Right? Now, if you had any complex conjugate pairs of zeros, right? If you remember from our previous video, we also discussed what that sort of looked like in standard Bode plot form, right? That would look something like s over omega, and let's call this the first z1, right? This is the first pair of complex conjugate pairs, z1 squared, oh sorry, this should be a squared, right? S squared over this plus 2 zeta z1 all over omega n z1 s plus 1 here, right? And what that ended up doing is you pulled out the omega n squared in the front here. So out here you would get like an omega n z1 squared, right? And again, this is just for one complex conjugate pair. You would do it for all of them, and I'm running out of board space, but I think you would see how to expand this here, right? If you had another pair of complex conjugate pairs, it's just basically pulling out the omega n z2 here, right? So however many complex conjugate pairs you have, just make sure they're all written in this form. So again, the thing you want to notice here is all of these, the constants are 1 here for all of these Bode plot terms. And this is where people would make a mistake here, is not pulling out the 1 here, which is going to screw up your constant offset or your constant gain of the Bode plot at the end here. So it's not a major issue, but it definitely is a problem at some point. So you want to write it in this format here, right? Okay, so again, let me maybe highlight all these, and we'll say this is all of our complex conjugate zeros, right? And then you do the exact same thing with the denominator here, right? So this first pole of P1, you'd write it in this format, right? Which involves pulling out the P1 over here, right? And then S over P2 plus 1, and you pull out the P2, oops, P2, and then all the way down to S over P1 R for how, you might have a different number of poles than real zeros. You probably will here, right? So this goes all the way down to PR. And then you do the same thing for the complex conjugate pairs of poles, right? So now you want this to be written as S squared over omega n P1 squared plus 2 zeta pole 1 over omega, the natural frequency of this first complex conjugate pair, times S plus 1, etc., 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 right? So you get omega n P1 squared, right? And again, these terms here are your real poles, and then here are your complex conjugate poles. And you might have a couple of poles at the origin here, or poles at the, you would probably have zeros, either zeros at the origin or poles at the origin here, right? You still could have an integrator or differentiator, but you probably don't have both at the same time, otherwise they would cancel out. So you could generalize this, but what I'm trying to get at here is if you look at this now, this entire gobbledygook over here, right? All of these constants, this whole thing becomes this constant gain K, so of your offset here, right? So really, you write this whole thing as your transfer function is some ugly mess of constants here, right? And then everything over here is all written in the nice exact format that we had explored last lecture here, right? We now know how all of these zeros contribute and all of these poles contribute and how this constant offset it contributes. So once you have it factored and written in this standard Bode plot form, step 3 is actually pretty simple here, right? So step 3 is just sketch the Bode plot of each one of these contributions by themselves here, right? So sketch Bode plot contributions for each individual component, basically by themselves, right? Okay, so you could sketch a Bode plot for a constant offset, for a constant gain K. You would sketch a Bode plot for just this zero, just this zero, just this pair of complex conjugate zeros, etc., etc. And once you have all of those Bode plots by themselves, you just need to linearly add them together here. So the last step here is add all components together linearly to obtain total Bode plot. Right? Okay, so I think what would help here is let's go through a concrete example of this here to see how we would do this. Okay, so let's look at an example of this. Okay, so let's say you start with the transfer function, again, in just numerator over denominator polynomial format. How about 50s plus 5 all over s squared plus 30s? Okay, so that's our transfer function here, right? Okay, so let's just go through our steps here. So step 1 here, right? This was factor to identify poles and zeros, right? So in other words, I want to factor the numerator and the denominator, so I'm going to write this thing like this. I will write this as 50 times s plus 1/10 all over s plus 30. Okay? So right here we can go ahead and identify that this thing is made up of actually 4 components here, right? You see that there is a constant, well actually hold on, we better be careful. I'm jumping the gun. Let's go through our process before we actually identify the components, because I almost made the exact same mistake I was just warning everyone about here. The constant offset, the constant gain, it's actually not 50, and we're going to see that here in step 2 when we write this thing as in standard Bode plot format here, right? So let's go ahead and do that now. So step 2, right? I want to write in standard Bode plot format. Okay, so what I've got to do here is, all right, I got the 50 here. Now, this first term here, I need to turn this into an S, well, I guess it's a 10s, plus 1, right? And what that means is I pull out a 1/10 on this side. Would everyone agree? I haven't messed with the numerator. Oh, okay, but I've written it in, this is now in standard format. Same thing with the bottom. Let's write this down, the denominator here. So this is S here. Well, I don't have to change this pole at the origin. That's already in standard form, but this is not. I need to write this as S over 30 plus 1, and then pull the 30 out over here, right? Great. So now what we see here is here's the constant. Right? It is definitely not 50 here, right? In fact, what we end up with here is I write this whole thing, the transfer function can be written as, this actually comes out to 1/6 here, times 10s plus 1 all over s over 30 plus 1. So this thing is now in standard Bode plot format here, right? Where every single one of these components look exactly like something we discussed last lecture. So now we see this thing is made up of 4 components here, right? So let's write down what these 4 components are here. So component 1 is a constant gain of 1/6 here, right? It is not a constant gain of 50 that you might just think of when you look at the transfer function. We had to go through the standard Bode plot format to see that it's actually a constant offset of constant gain of 1/6 here, right? Okay, what else is this thing made up of? Component 2 here, right? This is a real 0 at s is equal to minus 0.1 or minus 1/10, right? That's where the 0 here is. Okay, component 3. This is a pole at the origin, right? That's this component here. And then finally, component 4 is a real pole at s is equal to 30, or negative 30, excuse me, right? That's this pole right here. Okay, so now what we can do is let's go through and do step 3 where we look at each individual component. Actually, you know what we're going to do here is let's do steps 3 and 4 kind of together. So what I mean by that here is let's go through now and let's look at one of these components here and we'll sort of build up the mega transfer function as we go along, right? Because we talked about it earlier. All you need to do is linearly add each one of these components. So let's look at first component 1 by itself, then let's look at adding component 2, and then we'll look at adding component 3 and then adding component 4 to finally get our complete transfer function. So tell you what, give me a second to erase the board and maybe sketch up. I'm going to draw up a template of some blank Bode plots that we can start to fill in. Okay, so I've gone ahead and set up some blank axes for a Bode plot. And what I'd like to do right now here is down here on the bottom here, we are going to look at the Bode plot for an individual component. So this bottom left corner is, we're going to plot the magnitude in decibels of an individual component. And then on the bottom right side, we'll plot the phase again of that individual component. And then what I want to do here on these top 2 sets of graphs is look at building up the overall original transfer function, which we said here, and we will slowly augment each one of these components and linearly add and build as we go here. So we'll see how we can kind of create a Bode plot for this complex transfer function by just looking at each one of these components one at a time here and building them and adding them together linearly. So let's go ahead and start with component 1 here, right? So component 1 was the constant gain, right? And we said that the constant gain was k of 1/6 here, right? So the first thing we need to do, if you remember here from our discussion last time where we were talking about individual components, we saw that a constant gain is really, really simple. All it does is it shifts the Bode plot, or it's a constant line in magnitude of magnitude 20 times log base 10 of k, right? Which is 20 times log base 10 of 1/6. And if you crunch those numbers, this comes out to something like minus 15.6 decibels here, right? And then the phase of g of j omega it's just the phase of 1/6, which is a real number. So this is just 0 degrees, right? So the individual Bode plot is really, really simple. It's just a constant line here at a magnitude of minus 15.6, and I'm going to kind of butcher this a little bit here. That's not exactly right, but you can kind of see I don't want to draw over those lines here. There, and then a constant 0. Right? That's all this Bode plot is. So let's look at the total Bode plot. The total Bode plot so far is just this component. So let's write it up here. And what I've got actually is I made myself a little bit of a prop here to kind of help us when we are going to be modifying this a lot here. So what I want to do here is I want to put a constant line here at a magnitude of around minus 15.6. And again, sorry, I apologize. This is going to, well, let's try this. I guess I made my string a little bit too long here. But okay, so this is a total magnitude plot, which again, it's I take component 1, I linearly add it to nothing, I just get that. And then the phase here is just a constant 0 for all time. Okay, there we go. That's what my phase looks like. Okay, and we will come back to this in a second, and hopefully this is going to look a little bit cleaner here. Okay, so now we got the first component. Let's go ahead and do component number 2, right? What was component number 2? Component number 2 here was our real 0, right? So the next component here was our real 0 at s is equal to minus 0.1 here. So if you remember, the rules for sketching a real 0 here is what? Is that the magnitude stays at 0 until omega of about this 0 location, right? So 0.1 rads per second. And then it breaks up at positive 20 decibels per decade. Right, that was the rule. And then what does the phase do for a real 0? So again, if you remember our lecture last time where we looked at individual Bode plot components, we know that the phase stays at 0 until what? 0.1, 1 decade before the location, right? So this is at 0.01 rads per second, right? And then what does it do? It basically goes up to positive 90 degrees at 10 omega, right? So 1 decade after that 0 location here of, let me see, so that is 1 rad per second, right? So that's sort of the trend here. So again, let's go ahead and let me erase this because I want to use the green line for, again, looking at our individual Bode plot components. So let me try to see if I can carefully erase the green line. Okay, so the individual Bode plot for component number 2 here is what? Let's go ahead and sketch it. So the magnitude stays here at 0 until we get to 0.1, 1 decade before the 0 frequency. So tell you what, let's go ahead and maybe first, maybe it will help us if we sketch out again. Here is omega here, right, of 0.1 rads per second, which is the 0 location here, right? So this, and maybe what we should do is let's follow this all the way up. Okay? So what happens is for the magnitude, right, for the individual component, is that it comes along here at 0, right? And then when we get here to the actual location, this is going to start going up at 20 decibels per decade here. So this slope again was positive 20 decibels per decade. Okay, and then the phase, again, let's go ahead and identify right? This is the omega of 0.1, and then we're just looking 1 decade before and 1 decade after, so the phase will start at 0 until 1 decade before, right? And then it's going to go up, and then eventually we're going to get to here 90 degrees of phase at 1 decade after the 0 location. So this is our sketch for the phase. So all we need to do now is take this component and we're going to add it to what we had earlier. Okay, so all we need to do here is it still stays here at negative 15.6 decibels, but then when we get here to this frequency, it's going to start going up at positive 20 decibels per decade here. So let me see if I can get this. So 20 decibels per decade, that's about, okay, so minus 15, yeah, so maybe like here, and then 50, okay, so something like this. So let me see if I can kind of, this is why I made this little string here, so we can kind of try to move this thing. There we go. Okay, so this red line now is sort of the combined Bode plot, right, of component 1 plus component 2 gets you this here. Similarly here in the phase, so this is still component 1, so actually this is really simple. Since this is a flat line at 0, I just need to make it look like this one. So now all this is going to do is kind of go up to 90 like that, and then go across like such. Okay, let me see if that. Sorry, this is not the best, but I think you get the rough idea here, right? Okay, so great. That's component 1 and component 2. Tell you what, give me a second to now erase the board. I'll get rid of component 1 and actually, sorry, this was component 2, and then we'll move our way onto component 3. All right, so let's move on to now component number 3 here, which we said was our pole at the origin, which was another word for basically an integrator, right? Now, we said that the rules for the integrator is actually pretty easy, right? The magnitude is basically a constant line with slope of minus 20 decibels per decade, right? And it goes through 0 dB at omega is equal to 0 rads per second, right? And the phase was actually pretty simple for an integrator. Remember in our last discussion we said that the phase is a constant minus 90 degrees. So we can go ahead and draw that here. So again, down here in our bottom plot showing what that individual component, right, just the integrator. So the integrator, it goes through the point of 0 decibels at 1 radian per second, and otherwise it's just a slope, a line with a constant slope of minus 20 decibels per decade, right? And this just goes the whole way, right? And similarly, the phase angle was actually really simple. It's just minus 90 degrees for all frequencies, right? Okay, so now what we need to do is add this component linearly to the component up top here, right? Because right now the red line represents component 1 and 2. Now I want to make it represent component 1, 2, and 3. So we got to add this to this. So this is a little tricky. Maybe the easiest thing to think about here is look at the point here at omega of 1 radian per second, right? At that point, actually, the magnitude plot is not the magnitude plot of the integrator is not changing anything, right? So this point should stay the same. The red dot should be the same. It should not be affected at all. So this is going to stay fixed. So I kind of want to put a pin in here so this can't move. But everywhere else, what I need to do is I need to add a constant slope of minus 20 decibels per decade everywhere, right? So what we can think about here, right, is, okay, this doesn't change here. Right now, component 1 and 2 give you a slope of positive 20 decibels per decade. And now by linearly adding component 3, we're going to see that this negative 20 decibels per decade will cancel this positive 20 decibels per decade. So this will just become a flat line, right? Something like this. Oh, whoops. Sorry, I took my, hold on. We'll come back to that in a second. All right. And now what we have to do here is coming backwards. What do we have here? So here, again, this part will cancel, right? Right now there's a slope of positive 20 decibels per decade, and this small range for this 1 decade here, this will also cancel, but this will bring the entire thing up like this. And now this used to be 0, but now it's going to be, okay, so now it's going to look something like this, right? because it used to be flat, and now this constant -20 is also going to come up. So there we go. So now this red line should represent the magnitude for component 1, 2, and 3. Now let's come over here to the phase, and sorry, I took down my, let me see if I can put back the red line. I had to take this down because I was making some repairs to it in between the takes, so hold on. Let me go ahead and put it back to where it was. So this is what it used to be for components 1 and 2. Right, so I think this is what it sort of looked like for just component 1 and 2 by itself, right? And let me see if I can make this a little bit nicer. Okay, so this was component 1 and 2 by itself, right, where it was a 0, then at 0.001, it started breaking up up to 90 degrees here at 1 radian per second. So now all I need to do is I need to linearly add on a constant -90. So this is super easy. This whole line just shifts down by 90 degrees. So all I got to do is just pull this thing down by 90 degrees to make it look like that. There we go. Oh, great. I wish this thing was a little bit easier to deal with. Come on. Maybe let me put it like this. Sorry, I am butchering this. I envision this going a lot smoother in my head with this line I could move around, but maybe it's not really. Okay, so again, here we go. Now, again, the red line should be all 3 of these here, right? So 10 to the -1, 10 to the -2, 10 to the 0. Okay. Great, so I think that looks about right here. So -90, and then at 0.001 it starts coming up, and eventually comes up to 0 degrees here at 1 radian per second. Okay, great. So that's component now 1, 2, and 3 represented. So again, let me pause the video, erase the board again, and let's do component 4. All right, so let's come on over here to our last component here, right, which was just our real pole at S is equal to -30, right? So we remember that the rule for this is the magnitude stays constant at 0 until omega is equal to the break frequency of 30 here. Then it breaks down, right, at -20 decibels per decade, right? And then the rule for the phase here was that, again, it stays constant at 0 degrees until, until 1 decade before, right? So 1 decade before 30, which is 3 rads per second, right? And then it eventually goes to -90 degrees at omega is equal to 1 decade after the frequency, right, which was 300 rads per second. So we lose 90 degrees of phase over a period of basically 2 decades. So again, let's go ahead and do that. So over here on the magnitude plot, let's go ahead and sketch our individual component for just that pole. So first off, let's find the frequency of 30. So that's somewhere around here, right? So here's omega is equal to 30. Okay, so maybe also let's just draw this line straight up so we can kind of see what we need to get up here. Okay, and then we saw that the magnitude is pretty simple. The individual component, like we said, stays 0, 0, 0, 0, 0, 0, 0 until we get to here. And then all it's going to do here is break downwards at -20 decibels per decade here, right? So here we go, -20 dB per decade. Great, so that's the individual phase magnitude. How about the individual phase? So again, let's go ahead and find ourselves the break frequency, which was 30 rads per second, right around here. Okay, and let's go ahead and translate that up to our overall plot so we can use it. Okay, and the rule here was, again, 0 until we get to 1 decade before the break frequency, and then we are going to now lose 90 degrees of phase over 2 decades, like such. So here we go. So we play the exact same game we did before. We now need to go ahead and linearly add the green line to the red line. So all this is unchanged, right? Everything is unchanged until you get to this point, at which point we need to add this green of negative 20 decibels per decade to this. So all we're going to do now is this portion of the Bode plot is going to come down now at 20 decibels per decade. So there we go. Perfect. So now we basically have this red line should represent the Bode plot for components 1, 2, 3, and 4 all together at the same time. So that's pretty amazing. Do the same thing for the phase here. So again, unchanged until 1 decade beforehand, which is about here-ish. And now what it's going to do is we're going to start losing up to 90 degrees of phase over the course of a few decades. So something like that is, I think, sort of what we end up with here. I wish I could make this thing go away. There we go. So here we go. So at this point, we've got now the Bode plot. This thing doesn't go away. Where's my scissors? Cut this thing off. Let me cut this off. Make this a little bit. There we go. All right. Okay. So something like that. So hopefully now the red line is about what we've got here for the entire Bode plot for, again, components 1, 2, 3, and 4 all put together. And we saw the way we got this is just by linearly adding individual components up one at a time to get the overall composite Bode plot. So if you don't believe me, let's run over to MATLAB and just double check that this is actually what the Bode plot looks like. So again, take a snapshot in your mind of what this sort of looks like, right? It sort of comes down at minus 20 decibels per decade, and then here in between here and here, it kind of stays flat and then goes down again. And then for the phase, we just start at minus 90. We kind of have this bump up to 0 phase and then back down to minus 90 like such. So let's run over to MATLAB and verify numerically that our approximation or our sketches is actually pretty accurate. All right, so here we are. Let's go ahead and verify our Bode plots using MATLAB. So let's go clear CLC, close all, and then if you remember, let's go ahead and first define the transfer function. And in our case, I think we said our g of s. Then this looks something like, what was our original g of s here? I'm trying to remember here. Oh, I think it was 50s plus 5 all over something like, what do we have? It was like s squared plus 30s, right? That was our original transfer function. So let's go ahead and define it right now. So let me see. The numerator should be, what is it, 50 and then a 5, right? And then the denominator should just be a 1, a 30, and a 0. Great. So here's our transfer function. And now let's just go ahead and plot the Bode plot of this guy. And we'll turn the grid on, and we'll maybe give it a title here of Bode plot of complex transfer function. Okay, great. So let's just go ahead and run this script here. And again, here's our transfer function. And let me pull over the Bode plot, and here we go. And if you look at this, this looks amazingly similar to what we sketched up on the board here. So again, it drops down to minus 20 decibels per decade, but then there's flat spot in the middle, and then it starts to drop down a little bit. The phase, similarly, starts here at minus 90, bumps up, kind of almost recovers to 0, and then kind of bumps back down to minus 90 at higher frequencies. So again, this validates that the procedure we used on the board actually is very, very good. So what I'd like to do now is actually, this is all fine and dandy and great that we're able to decompose a transfer function into its individual components and plot a Bode plot, but this opens up, if you think about it, a whole new world of possibly how you could shape the frequency response of a transfer function or a given system. So let's hop back over to the board here to have that discussion. And before we leave this Bode plot, what I'd like to investigate is, let's assume here the frequency is at about 100 radians per second. So right here, we can look this up and notice here that at a frequency of 100 radians per second, this system has a gain here of negative 6.4 decibels. So keep that in the back of your head here, and let's hop to the back of the board, back to the whiteboard, and take a look at some next steps. Okay, so we validated that our sketch of our complex Bode plot is actually fairly accurate. And what I wanted to talk about now is almost do a little bit of a teaser into the concept of loop shaping or frequency domain shaping here. Because now, hopefully, you can see that we can affect the Bode plot of a system by looking at how the individual components contribute. So, for example, coming back to our original transfer function g here, right? what if this represented something like, maybe it's like an actuator on an aircraft or something like this. So, for example, maybe this describes a frequency response of how, like, the elevator responds to a command. So this could be like delta elevator actual over delta elevator command. So again, just for those of you who might not be aerospace related here, what I would mean by that is, let's say you've got some kind of aircraft here, right? And the elevator is this control surface on the back, and you want this thing to deflect up or down so that you can pitch the aircraft up or nose down here, right? And maybe you want to be able to have this thing controlled at some sort of specific frequency, or you need it to be able to actuate at a certain frequency range here, right? So what you could be thinking about now is, okay, this plant here, G of S, represents how the actual elevator responds to a command in elevator, right? And let's say this system has to operate at omega of 100 radians per second. And I think this is, I can't remember, I did the calculation, but in terms of hertz, I think this is something like, I don't know, was it like 16 hertz or something like that? Yeah, this is approximately 16 hertz. Right? So you want this actuator to be able to flip up and down quite quickly, right? But now you saw in the MATLAB script, and actually we can read it off of our plot here, where is that point of 16 rads per second? That's right here, right? So the problem here is, or sorry, the input of 100 radians per second, which is 16 hertz, that's right here. But we see here that the Bode plot at that point, I think we said this was minus about 6.4 decibels, okay? So what does that mean here? What's going on? So what this means is 20 times log base 10 of the magnitude of G of J times 100, right? So this was at 100 radians per second. This was negative 6.4. If you solve this for this magnitude here, right, you get magnitude of G of J omega, or sorry, G of 100 omega, right? 100 omega, 100J, excuse me, right? This comes out to, I don't know, 0.4, what was that? 0.48-ish. So what this means here is you command the elevator to go to a certain deflection or at some rate here. It's doing less than half of this, right? So if you're commanding the elevator to do this, right? And you want this elevator to go between 30 degrees and negative 30 degrees at 100 radians per second. What actually comes out the other end here is half of that. And again, I guess we could also look at the phase at that location here to figure out exactly how out of phase it is. But I think you'll get the picture. I'm not going to be able to draw this accurately here, but I just wanted to make sure that we kind of see what's going on. This is my horrible artist rendition here, right? The elevator or the actuator doesn't go to the location you specify here, right? So one thing you could think about doing here is, all right, could I maybe add another component here? Let's call this maybe a C of S. It's something I'm going to add here. So this component here, if you remember our discussion on block diagram algebra, since these two things are just in series, it's almost like this is another component to this transfer function here, right? So you can think about, well, what's the problem here? The problem is that I need this thing to bump up by 6.4 decibels at this range. In other words, I really would like it if I could get another component here, like this C of S, which has a frequency response of something like, I don't know, it's got something here, you know, something here, whatever, but at 100 radians per second, what I needed to do here is I needed to sort of bump up by 6 decibels. So this would be positive 6.4 dB. And then it could do whatever the heck it wants, something like this, right? So the other way, we can go around this sort of backwards and say, here is the component I need to add. This is the frequency response of the component I need to add. What type of transfer function will get me that? Well, again, luckily, if you watched our previous discussion, we saw that this looks a lot like a pair of complex conjugate poles. A pair of complex conjugate poles with some damping ratio between 0 and 0.707 will get you this hump, and we can place this hump exactly where we want it to. So for example, like just to go through with this, this discussion completely here, let's just do a few more calculations and see if this works. So you remember earlier that what we basically need here is we need a pair of complex poles, complex conjugate poles, we need its resonance frequency to be exactly 100 rads per second, right? And what we need here is with a magnitude of positive 6.4 decibels at this resonant frequency, right? So I want to figure out what is the transfer function that will get me this frequency response here that I showed here in green. So again, if you go to our discussion earlier, you remember here from our lecture on resonant frequencies, we said the resonant frequency here of a dynamic system is the natural frequency times square root of 1 minus 2 zeta squared. And what I need this to do is we need this to equal 100 radians per second, because that's where I want to add this bump here. And now we also saw that 20 times log base 10 of magnitude of g of j omega for a pair of complex poles here, or sorry, omega r. Let me write this out again. G of j omega r, right? This is how much bump, or the magnitude of the bump of that complex conjugate pair here, right? We said this was given by minus 10 times log base 10 of, oh boy, I'm running out of space. I'll write it down here. Minus 4 zeta squared times zeta squared minus 1. Right? Maybe let's make these square brackets so you can kind of see where the log 10 starts and ends. Right? So again, this was from our discussion here of resonance frequency. And again, what we want here is we want this to equal 6.4 decibels, right? So great, you basically just solve these simultaneously. In fact, this is probably the easiest one to solve first because there's only solving for zeta here. So you solve this for zeta and you can come out, there's actually 4 solutions here, but the only one here that is in the range of 0 to 1 over root 2, right, which is where we said we get these bumps here. This is a zeta of about 0.24-ish. And then you can use that to solve this here because we know that we want this to value to 100s and we know zeta is now 0.24, so we can solve for what's the desired natural frequency. And if you solve for that, you end up with a natural frequency of 106.7-ish or something like that. So great, now what we know is we know that if we add a component here with this natural frequency and this damping ratio here, it will get us this type of a response here. So just to be completely explicit here, so what I'm going to add now is this C of S component, the thing that we're going to add in series to this actuator we were talking about, is just something like a 1 all over S squared over omega n squared plus 2 zeta over omega n s plus 1. Right? And here you just plug in your omega n and your zeta that we talked about over there. So you can think about just, if you just build this little electronic component and you add it right beforehand, it will add this type of a frequency response to the system here. And what is the magnitude going to look like? So now we better go ahead and do this. So what it should do here is basically stay unchanged until you get here, and it will add this bump. So it will bring this part of the Bode plot up to around 0. Oh, sorry, so something like that, right? So we'll shift the whole thing up by 0, and actually, then it's going to, unfortunately, the price you pay for that is this slope is going to get steeper by 40 decibels per decade here, right? Because now this slope here is negative 40 decibels per decade, right? And I guess if we want to make this this completely accurate, maybe what we should do is we should also talk about the phase. So remember, the phase approximation for this pair of complex conjugate pairs here is it should what? It should come here. Where's our natural frequency? Right here. Maybe let's use the same color we were using earlier, which was red here. So here's our natural frequency of 100 radians per second. So it's going to stay here at 0, 0, 0, 0 until 1 decade before, and then we're going to actually end up losing 180 degrees over the course of 2 decades. So we'll do this, right? So I need to add this to this phase plot. So here at 100, this thing starts actually coming down pretty significantly. So instead of 90, so we'll actually end up, oh crud, I shouldn't have cut off the end of this thing, because now I need a little more red, because eventually this thing is going to come all the way down to 270 degrees, negative 270 degrees of phase that we're going to lose. All right? Okay, so again, let's run over to MATLAB and just verify that all this looks reasonable. All right, so here we are. Let's go ahead and now add C of S, right, which was this additional compensator, this additional system that we would hope fixes this problem at 100 radians per second. So again, let's go ahead and define our damping ratio that we said. It's about 0.24-ish, I think, was about what we calculated, and the natural frequency was about 106.7, okay? So the numerator for this compensator is just 1, right, and then the denominator for this compensator was 1 over omega n squared, right, and then 2 times zeta over omega n, and then a 1. Okay, so this is our system here. So here's our transfer function representing the extra component. And now what I can do is just go ahead and make a Bode plot of G of S and C of S in series, like we drew up on the board. So in other words, what I want to do is do something like, I don't know, G total or something like that, which is the two of them, is G times C, right? And then we'll go ahead and say figure Bode of G total. Grid on, and let's maybe give this thing a title of G of S and C of S in series. Great, so let's go ahead again and run this script. So, again, here is the original Bode plot of just the plant G of S by itself. And we see, right, here was the problem. At 100 radians per second, we got this attenuation here, and you're not getting the same output as you are putting in the input. And now, here is the two of them in series, and we see, look at this. This did fix the problem, because here at 100 radians per second, we're getting very close to 0 decibel. And in fact, we should be getting exactly 0. I think due to some of the numerical round off is causing a bit of this issue here. So if you want to double check this and verify this is working as well, what we can do here is, tell you what, let's go ahead and fire up Simulink. Okay. And I've actually got myself a model that's kind of halfway built already here that would illustrate this. So let me go ahead and grab that here. So here's this model that would help show what's going on. Let me zoom in a little bit so we can see what's happening. Okay, so into this is a sine wave. Let's go ahead and make this sine wave, I don't know, let's call it 2 radians per second, and the frequency we care about is the amplitude is 2. So in this case, this might mean 2 degrees, right? Because this is like the input command to the elevator, and we're actuating it at 100 radians per second. Now, the top path here is just the original system by itself, right? So the original system by itself is going to potentially have issues because at high frequencies, it's not going to be able to track this. Let's change a couple of these parameters just to make sure we're all on the same page here. I don't know, let's simulate for, I don't know, just 2 seconds, how about? And tell you what, I'm going to change a couple of these other parameters just to make sure that we, okay, so the max step size, let's take some small steps here so that we don't miss any dynamics here. Then let's go ahead and see if we can run this. And again, let's look here at the top scope. And if I grab that, oh, this is kind of hard to see. 2 seconds is too long. Let's run for, how about half a second? Try that again. Okay, so here we go. Look at the top scope, and we see that indeed the yellow is the input sine wave, and the blue is the output sine wave. So we are commanding the elevator, well, and again, see, we should be going to +2 to -2, but you can see the time steps we're taking are too big, we're missing things. So tell you what, let's change the time stepping again here. Let's come up here to the configuration parameters, change this to, let's go another order of magnitude slower. 0.001 is the max time step we'll take. All right, save the model, run it again. Let's take a look at the scope. There we go. That looks a little bit better. Okay, so the input sine wave is, yeah, ±2 degrees. You're telling the elevator to actuate to +2 degrees, then -2 degrees, and +2, then -2. But what the elevator is actually doing here is you're only going to less than half. So it's going +1 to -1. So that's a problem. But now, when we take that same system now and add that compensator that we talked about, or that little component where this is basically just those two complex pairs of poles, and we run the exact same input to it, let's look at the output here. So I'll open up the second scope here. And here we go. And now you see we kind of fixed the problem in the sense that you are commanding plus and minus 2 degrees of elevator, as you see in the yellow. And we still get plus or minus 2 degrees, as you see in the blue. So this has fixed the problem effectively. So with that being said, I hope you enjoyed the video today where we discussed how to decompose a complex transfer function into its constituent individual pieces, and then understand how the Bode plot of the overall system is made by just linearly adding the Bode plots of all of the individual parts one together. So we'll be talking a lot more about this in the future. This leads into a discussion of loop shaping, notch filtering, lead lag compensators, all of those kind of good topics we're going to be covering in the future. So if you don't want to miss any of these videos, please subscribe to the channel and let me know what you think about this video in the comments below. It really helps me continue making these. And until we catch you at another video, I'll talk to you later. Bye.